everyone. So today we're doing lesson 4.6 on geometric sums and applications. So first I'd like you to do a warm-up exercise. We've got two problems, one where you're evaluating a series that's given, and two where you're writing the series in sigma notation. So go ahead and pause the video now, take a few minutes to work these problems, and then come back whenever you're ready. Okay, welcome back. So on number one, you should have had 344,399 for your sum. For 2a and b, whenever you wrote your series in sigma notation, remember we're going to start with n equals 1. Then we're going to make sure we have the correct rule. You see a is arithmetic and b is geometric. And then that top number, that's the last n value you plug in to get the last value. So let's review just the solutions to these in case you need a refresher. For the first one, since I notice that I have an arithmetic rule where the common difference is 3, I know that my sum is going to be equal to the total number of terms, which is 478 over 2, times the first term, so plug in n equals 1 and you get a 5, plus the last term, plug in 478 and you get 1,436. So when I multiply that out, I get my answer, and my sum is the 344,399. For A, whenever I'm writing the series in sigma notation, first I have to make sure that I recognize that it is arithmetic. As I'm going from term to term, I notice they're all increasing by 3. So my common difference is 3, and my starting value is -7. So when I'm writing my rule, a sub n will be equal to 3n, and then I like to think about what would that 0th term be. If I went back a term and I subtracted 3, my 0th term would be a -10. So I need to subtract 10 so that when I plug in a 1, I would get that first term of -7. And of course, you could always reuse that rule a sub n equals a sub 1 plus d times n minus 1 if you would like. So when I'm writing my series notation in sigma, my series in sigma notation, I have my rule here, and I start with n equals 1. So the last thing for me to determine is really what n value gives me that last term of 104. So I'm really solving 3n minus 10 equals 104, and when I solve for n, I get the 38. So now I'm going to plug in n equals 1 and all the way up to 38 to get my series. Now the next series, as I'm looking at these terms, I notice right away that it's not arithmetic, because to go from 2 to 14 you need a 12, and then to go from 14 to 98 you need a lot more than 12. So it's not arithmetic. So now I'm checking if it's geometric. 2 times what is equal to 14? It would be 7. So let's check and make sure that this checks out. 14 times 7 is indeed 98. Multiply again and I get the 686, so I can see my pattern is geometric with a common ratio of 7. So when I'm writing my rule, I have a sub n equals my first term times 7, my common ratio, raised to the n minus 1. So that's my rule here. I started with n equals 1. If I plug in, let's just check real quick. If I plug in n equals 1, let's just make sure I get 2. So when I plug in that 1, I end up with the 7 being raised to the 0, and 7 raised to the 0 is just a 1, and 2 times 1 is indeed 2. So my rule is going to work. So now I need to figure out how did I get that 8? And the way that I figured that out was I'm going to erase some of this because I'm running out of space. I'm going to erase this. I set this right here equal to my rule. So 2 times 7 raised to the n minus 1 equals 1,647,086. I divided by 2. So then I just had 7 raised to the n minus 1 equals this 823,543. And now I had to use my calculator. To solve this, I'm going to need a logarithm, but I haven't taught you logarithms yet, so we're not going to do that quite yet. We're just going to plug in different n values and see what makes this true. So when I plugged into my calculator 7 raised to the 7th, 7 raised to the 7th was equal to that 823,000 number. So that means that n minus 1 had to be equal to 7. And if n minus 1 equals 7, that means my n value is 8. So that's how I got that last value. So this is just a little warm-up to refresh our memory on a lot of the things that we've learned so far in this unit. Today we're going to learn how to do sums of geometric series and some application problems. You guys know how to find sums of finite arithmetic series because we learned about that already. But what about finite geometric series? So remember that notation, S sub n stands for the sum of the first n terms of a series. So if I'm looking for the sum of the first n terms of a series, and my series is a finite, so terminating, geometric series, it is going to be equal to a sub 1, which is just the first term in the series, times this ratio of 1 minus r. R is my common ratio, raised to the n, where n, again, is the total number of terms I'm adding up, all over 1 minus that common ratio again. You are definitely going to need a calculator because remember from our mom versus dad exercise that geometric series grow much, much faster than arithmetic series do. And so these numbers get quite large quickly. So I want to evaluate the series from t equals 1 to 16 of 4 times 3 raised to the t minus 1. Let's just write out a few terms just so we can see what's happening. If I plug in a 1, I'd get a 4. If I plug in a 2, I would have 4 times 3 raised to the first. If I plug in, this is a t equals 1, t equals 2, t equals 3. So I'd have 4 times 3 to the second. Let's just go one more out. So I'd have 4 times 3 cubed, dot, dot, dot. So I can simplify some of this. I would have 4 plus 12 plus 36, and then 4 times 27 plus da da da. And I know that I am adding up all the way until I plug in t equals 16, so 16 total terms. Not completely unreasonable to do by hand, but there's a much faster way by using this formula that I have. So I know, based on my formula, that this sum will be equal to the first term, a sub 1, which is 4, times 1 minus my common ratio, which is 3. That's what I'm multiplying by every time. You see it right here. Raised to the total number of terms, which is 16, all over 1 minus the common ratio. Now, when you're plugging this into your calculator, you can get this formula right, but then you could plug it into your calculator wrong. So let's make sure that we are good with how to do that. The way I like to do this is I like to plug it in steps. So first I plug in the 1 minus 3 raised to the 16th, and I hit enter. Then what I do is I hit divided by, so that I get that answer, and it should pull the answer. So you hit divided by, and then make sure you have parentheses around this if you're going to type it in as it is. So divided by parentheses, 1 minus 3, end your parenthesis. And then since that's easy, you could say just divided by -2, and no parentheses are necessary. And then what I like to do is I take that answer, so I just hit times this first term, 4. And that guarantees me that my answer is that I've done this order of operations correct, my answer is correct. So I get 86,093,440. That is the sum of these 16 terms. So you can see how quickly those terms grew in order to get a sum that is that large. Let's do another one. So here I'm given a sequence where p sub 1 equals 7 and p sub n equals p sub n minus 1 times 4, where n is greater than 1. So here I notice my first term is 7, and here this says I'm taking the previous term and I'm multiplying by 4. So I know this is a geometric sequence such that the common ratio is 4, and the first term, which I named p sub 1 instead of a sub 1, is 7. So my explicit formula for my sequence, p sub n, will be equal to the first term, 7, times 4 raised to the n minus 1. And now I want to evaluate the sum from n equals 1 to 34 of p sub n. So the sum from n equals 1 to 34 of 7 times 4 raised to the n minus 1. So since this is geometric, I now have a formula for this. I know that my sum is going to be equal to the first term times 1 minus the common ratio raised to the total number of terms that I'm adding up, which is 34, divided by 1 minus that common ratio of 4. Remember the order in which you plug this into your calculator. Plug in 1 minus 4 raised to the 34, hit enter, divided by parentheses 1 minus 4, and parentheses, enter, and then times 7. And this answer was incredibly large. I got 6.8867 times 10 to the 20th. So in scientific notation, remember that means I'm going to take this decimal, it would go back 20 spaces. It's going to be an incredibly large number. So that is how we find the sum of a finite geometric series, a series that ends. What I want to do is I want to consider a square with side lengths of 1. So I have a picture here, and you can see this is going to be 1, and this is 1. So if this is a square with side lengths of 1, then the area of this square is just 1 times 1, which is 1 unit squared. And we know that from geometry. Well, what if I were to take that area, which I know is 1, and I were to half this area? So what I'm going to do is I'm going to look at the square, and I'm going to cut it in half. So I'm looking at this piece right here. Well, that is only a half. Then I take the half that's remaining, I'm going to half that. So that area right there would be equal to a fourth. Now I'm going to take the fourth that's remaining, and I'm going to half that, and half of a fourth is an eighth. Now I'm going to take the eighth that's remaining, I'm going to half that, and that's equal to a 16th. Then I'm going to take half of that 16th, that's a 32nd. I'm going to do it again. I can keep doing this over and over and over and over. The question is, how many times can I continue to half this area? And the answer is an infinite number of times. Whatever my area is, I can always take half of it. Now these numbers are getting incredibly small, but I can always take half of a value. When I look at this sum that I've just written out for you in my different colors here, you can see that I've just generated a geometric sequence. I shouldn't say sequence. I have a series because I'm adding up these terms where my R value, my common ratio, is equal to a half. If I take 1/2 times a half, I get a fourth. And a fourth times a half is an eighth. An eighth times a half is a 16th, and so forth. I can even write a rule for this series. A sub n is going to be equal to the first term, which is 1/2, times 1/2 raised to the n minus 1. This is my first term and my common ratio. And I can write the series in sigma notation. You got n equals 1 times 1/2 times 1/2 raised to the n minus 1 raised to the infinity, because it's an infinite series. Now the thing about this is I have an infinite series. I will continue to add a number forever and ever and ever, and these numbers represent the area of this square. But I know the area of this square is 1, which we had right here. So what I have here is an example of an infinite geometric series that has a sum. So let that sink in for just a minute. And let's look at, in summary, at what we're saying here. We're saying that the area is 1, and it is also equal to the sum from n equals 1 to infinity of 1/2 times 1/2 raised to the n minus 1. Infinite series that has a sum. And there are lots of infinite series that have sums. They just have to have one key quality. So let's take a look at that quality. So I have a sum of an infinite geometric series if first it's geometric. Let's definitely check that box, infinite geometric. And if your common ratio, the absolute value of your common ratio is less than 1. And if those two things hold, then the sum of the infinite geometric series is equal to a sub 1 all over 1 minus r. So again, this is only for infinite geometric series where the common ratio is less than 1. The absolute value of the common ratio is less than 1, so you don't care if it's positive or negative. Let's take a look at a couple examples here. So I have evaluate the sum of the infinite geometric series I equals 1 to infinity of 5 times 0.8 raised to the I minus 1. So I notice that this is geometric form. Here is my first term, and here is my common ratio. So that means the sum is going to be equal to a sub 1, which is 5, all over 1 minus 0.8. And again, this only works because when I'm looking at this common ratio, 0.8, the absolute value of 0.8, is indeed less than 1. So when I'm taking a look at this and I'm simplifying, I end up with 5 divided by 0.2, and that gives me a 25. So here you have an infinite series with a finite sum. Now let's look at B. I have 1 minus 3/4 plus 9/16 minus 27/64. So I notice that this is geometric, and my common ratio is equal to negative 3/4. So let's check, is the absolute value of negative 3/4 less than 1? Well, the absolute value of negative 3/4 is 3/4, which is less than 1. So therefore, I know that since this is infinite and geometric, and my common ratio is less than 1, the absolute value of it, I know this has a sum. And the sum is going to be equal to the first term over 1 minus the common ratio, which is a negative 3/4. So I'm running out of space. Let me erase a little bit of this. Pause the video if you're going to need any of the scratch work we did as we were verifying that we could use our formula. And now I have 1 over 1 minus a negative 3/4 is 1 plus 3/4. That's 7/4. And 1 divided by 7/4 is 4/7. So the sum of this infinite geometric series is 4/7. So there are some examples for ones that are finite geometric and ones that are infinite geometric where you have sums. So the last 3 examples that I want to go through are application problems. So these could be geometric or they could be arithmetic. What you have to decide is which one is which and which formulas we're going to use. So first let's consider a pendulum that is released to swing freely. It travels 18 inches on the first swing. So here you can see it's traveling 18 inches. On each successive swing, the pendulum travels 80% of the distance of the previous swing. So a little shorter, only 80% of the original swing. So on the second swing, it travels the first swing times 0.8. So that's 80%. Then on the next swing, it travels its previous distance, which was 18 times 0.8, times another 0.8, so I get 80% of the previous swing. Then on the last swing, again, it's the previous swing. Now the previous swing, let's rewrite this as 18 times 0.8 quantity squared, just so that it's a little cleaner. So on this fourth swing, it's going 18 times 0.8 quantity squared times another 0.8 to get 80% of that swing. And when I clean that up, I get 18 times 0.8 quantity cubed. So the question is, what is the total distance that the pendulum is going to travel? Well, when I'm looking at this, I'm thinking, all right, I got to add up 18 plus 18 times 0.8 plus 18 times 0.8 squared plus 18 times 0.8 cubed. And how far do I go? I mean, I can infinitely take 80% of the previous distance. What is this sum going to be? Originally, I'm kind of thinking, well, if I keep adding numbers, this will never have a finite sum. But then I remember, oh, this is infinite and it's geometric. As I'm going from term to term, I notice I'm just multiplying by 0.8 every time. So therefore, my common ratio is equal to 0.8. Let's check and make sure that the absolute value of my common ratio is less than 1, and it is. So therefore, I know that the sum is going to be equal to the first term over 1 minus my common ratio. So now when I take a look at this, I get 18 divided by 0.2, and that is 90. And it tells me that the first swing was 18 inches, so I know my units are inches. So the pendulum will swing 90 total inches. Pretty cool, huh? All right, let's look at the next example. Elise is building a pyramid of paper cups. The bottom row has 72 cups, while the top row only has 1 cup. There are 18 total rows, and the number of cups on each row represents an arithmetic sequence. Find the total number of cups. So what I'm looking at here is I got a bottom row with 72. I'm not drawing 18, but I have this like tiered pyramid, right? Where I have 1 cup at the top, and I know I've got 18 total rows in the pyramid. Now they're telling me this grows arithmetically, so that means that as I go from 72 to 1, or you can think from 1 to 72, then the difference is going to be the same from layer to layer. They tell me this is arithmetic, so I know that the sum of an arithmetic sequence is equal to the total number of terms over 2 times the first term plus the last term. Well, think about how many terms you're adding up here. The terms here represent my rows. So I have 18 rows. My first term, my bottom layer, is 72, and my last term, my top layer, is 1. And you could interchange those two if you're thinking of 1 as your first layer and 72 as your last layer. It shouldn't matter. So then I just have 9 times 73, which gives me a total of 657 cups in this pyramid. It's a pretty big pyramid. All right, let's look at one more example. The amount of interest that Michael earned on his savings account for the past 3 years since opening his account is shown in the table below. So in the first year, he gets $72 of interest, the second year, $86.40, and the third year, $103.68. It says, determine whether the pattern represents an arithmetic or a geometric sequence. Then find the total amount of interest that Michael will earn after 25 years. So as I'm looking at this, first I have to determine if it's arithmetic or geometric. Well, right away, I know it's not arithmetic because the difference from 72 to 86 is less than the difference from 86 to 103, and it's pretty substantial. So now I want to check and see if this is geometric. So that would mean there's some common ratio that I'm multiplying by from term to term. So let's see what that ratio would be going from 72 to 86.4. Let's do 86.4 divided by 72, and I get a 1.2. So therefore I know that this right here would be 1.2. And let's check the next one. Let's check 103.68 divided by 86.4. Ooh, I get 1.2 again. So I know from this term to this term, 1.2. So that means, indeed, this is geometric, with my common ratio of 1.2. I even could write my rule. A sub n is equal to my first term times 1.2 raised to the n minus 1. And that would give me the amount of interest earned on any given year. So if I plug in n equals 25, that would tell me the interest that he earned just in that 25th year. But they don't ask me for that, do they? They asked me to find the total amount of interest that Michael will earn after 25 years. So they are asking me to discover 4, 5, 6, all the way down to 25. All of this interest, I would have to calculate that, and then I would have to add it up and find the total. It sounds like a pain. But then I remember I know how to find the sum of finite geometric sequences. The sum of the first n terms is equal to the first term times 1 minus the common ratio raised to the n, all over 1 minus r. So let's go ahead and plug this in for 25 terms, because I want to find the sum of the first 25 terms. So I'll get a sub 1, which is 72, times 1 minus my common ratio raised to the 25, all over 1 minus 1.2. Remember how you plug this in your calculator. First, plug in 1 minus 1.2 raised to the 25th and hit enter, so you can get that first numerator. Then hit divided by, parentheses, 1 minus 1.2, end your parentheses, and then times your 72, and you should be able to see that, wow, Michael has earned, over the course of 25 years, $33,982.60 over 25 years. So again, that is the sum, the total, if I add all of these up. So now you guys should be good to do problem set 4.6. And I hope you guys have a great day.